Welcome back. So, now we actually have an AFM in hand that is ready to scan, and let us now see how you can generate those awesome data using an atomic force microscope, or awesome images using an atomic force microscope. Please try to appreciate this statement that I made, that the discovery of the AFM in fact changed the perception of vision in many ways. Because as a part of this course you have already seen several atomic force microscope images, but none of them are actually photographs, they are data rendered images, and we will see how that how this data gets generated in somewhat more detail now. So, what we have, we now understand the basic components of an AFM. You have a tip, a cantilever, you have a laser source, you have a QPD, you have a feedback loop, and you have a scanner, right. So, the AFM is now aligned, it has approached, and it is therefore ready to scan. And so, now if we try to draw it here for our own understanding. So, the sample is now in place, you have the QPD because the laser source is there. So, I mentioned that approach can be achieved by either moving the sample from the bottom or the tip from the top. So, which would mean that in that case the laser source, the QPD and the tip move simultaneously. These three always remain coupled. There is deflection, therefore, the location where the reflected laser spot is falling can change. So, from this particular image, very simple looking image, of course, it is reflecting from the back side of the cantilever tip. Anything else you can comment? This is in fact the set point. Okay. So, now this cantilever which is mounted to the scanner is ready to scan. So, if we look, identify the area where it wants to scan, it has approached at this point, but you can choose that point, it can be the top left corner, right top corner, whatever, any of them, but it is one of the extremities. So, now what it is going to do? It is going to scan. So, it has to move first along, let us say this line. Typically what it does, it goes on collecting data at all the points over here, as it is, let us say, shown in this graph. It goes on collecting. So, here it shows that it as if it is starting from this point, it is all the same. So, it goes collecting data at all these points here, then it comes back, goes to the next level, collects all the points. So, it is a simple double do loop, and you have the option of choosing which way it will go. So, it can generate all the values of x equal to 0, 1, 2, 3, 4 for y equal to 0, then y equal to 1, y equal to 2, like that. Then your x becomes the fast axis and y becomes the slow axis. So, if the tip is moving like this and then slowly hopping from this location to this, then this is your fast axis, this is your slow axis, right. You can choose the motion to be like this. In that case, this becomes your fast axis and this becomes your slow axis. Modern AFMs in fact allows you to tilt the area you want to scan like this, and that becomes possible because most of the modern some of the modern atomic force microscope uses a cylindrical piezo, a single piece cylindrical piezo, but this was not possible, or this is still not possible where you have decoupled or separate piezos for the x, y and the z scan. This is something I will discuss in bit greater detail. So, anyway, now as the scan takes place, let us say we just exaggerate this view and examine very carefully as to what happens as the cantilever reaches from point 1 to point 2, and let us assume that the topography of the surface is something like this. So, what it means that the surface is rough and point 2 is at a higher elevation than point 1. It is shown in this particular figure in the transparency, but there is a bit of a mistake made in the location of the reflected light. So, I would request you to follow the ones that are here. These have all been made by me some years back for my course, but I made some mistakes while making the sketches. So, this is let us say the configuration of the cantilever at point 1, and this is let us say the point 2. We have just exaggerated the gap. So, this is the set point, and as you start to scan, the reflected light falls at the set point. Now, as of course, the picture has become a bit too complicated. As the cantilever moves from point 1, and also I will just redraw it. So, you have a surface like this. This is your point 1, this is your point 2, this is the deflection at point 1. You have the QPD. This is the set point. So, your reflected light falls at the set point. Now, as you raster, as you move from this point to this point, your tip reaches here. The end of the tip remains at the same elevation, and therefore, what is the consequence? The tip has now more deflection. It has more deflection. In fact, anyway, it has more deflection. The force is more. The figure is a bit wrong. I have drawn it a bit wrong. Anyway, so what is the consequence? Again, the sample can move or the tip can move, but if the tip moves, please remember it moves with its entire baggage. That is a laser source and the QPD. So, since the deflection has changed, now the reflected light is not falling at the set point, it is falling somewhere else. I will exaggerate this. This was my set point, and this is where reflected light is falling. So, what do you have? You in fact have an error. What is the error? The difference in the voltages between these 2 points. Now, what do? You actually feed this error to the feedback loop. And what does that do? Suppose this was the configuration of the cantilever at point 1. As the cantilever has gone to point 2, its deflection has changed. This is 1, this is 2. Please note that these two are at the same level, right. So, only the deflection has changed, and now as a consequence of this change in deflection, there is in fact an error that gets generated in the QPD. This error is fed to the feedback loop, which now inputs this error in voltage to the scanner, which is a piezo scanner. And what does this scanner now do? The piezo now becomes short and wide in such a way that the point at which the tip, the cantilever is mounted, goes up, so that the deflection now reduces and matches that at point 1. So, what would be the consequence on the QPD? the consequence on the QPD will be, as the piezo relaxes, piezo sort of or as the deflection reduces, light which was falling at this point, the laser again starts to fall at this point, because the deflection now, this let us term it as 2b, matches with the deflection of 1. Therefore, it is again falling at the set point. The deflection is again same as that corresponded to the set point, and again now with this new deflection, it is now ready to move from point 1 to point 2 to then to point 3, and at every point it goes like this. What you have learnt in the process, we will have a look here in the PPT, though the quadrants are wrong, but the basic essence is same. So, as the cantilever moves from point 1 to point 2, the deflection changes, and therefore, the laser light falls at a different location and not at the set point. This is the set point. In fact, I will use a different color of the ink, that will help. So, this is the set point, but as the deflection changes, it does not fall on the set point, it falls somewhere else. So, there is an error. This error is fed through the feedback loop to the piezo, and the piezo in fact becomes, in this particular case, becomes short and wide, so that the deflection of the cantilever or the force of the cantilever reduces, and the reflected light again falls back at the location of the set point. Had the surface, had the point 2 been at a lower elevation than point 1, then the error would have been such that the piezo would have deflected in a manner that it becomes long and slim, so that the bottom point of the bottom point where the cantilever is mounted to the piezo would have gone down. And all you do is you track this movement, upward or downward movement of this particular point at every x and y, and remember, this will have negative and positive values. The values will be with respect to this particular point where the cantilever approached, and that is the point. That is the point where the elevation, the height, will be considered as 0. Then this point will have some plus z value, a point which has lower elevation will have some minus z value. But if this is the point, this is the first point where the cantilever had approached, this will maintain to be some sort of z equal to 0. Okay. So, this is in fact what you have learnt is contact mode imaging of the AFM, the most basic mode. It has its own problems, because you are essentially dragging the cantilever while you are rastering. So, it is bad for both the tip and the sample, particularly for soft samples. Contact mode tends to spoil up the surface, it makes the tip very blunt. Those problems are there, but those are secondary things. So, we now understand contact mode, but we also need to understand what are the other modes. So, this picture now should make sense to you. This is the rastering option. So, it is in fact a nested do loop, nothing more than that. It is a nested do loop. So, you just go on gathering the data, and now you understand that after your complete scan is over, you are simply going to generate a data file like this, right. I will come back to this, but before that I should tell you something that I deliberately skipped at that point, and that is the scanning modes. So, primarily there are two scanning modes, the contact mode which you already know now, but there can be other modes like non-contact mode. In fact, the non-contact mode, the cantilever operates in this particular configuration. So, you are somewhere over here in the force curve, because the idea is same. Now, as the cantilever moves, as the points, as the surface goes further away or becomes closer to the cantilever, it can still change the deflection. It is scientifically very sound, robust, and very exciting also, because it does not touch the surface. It is really relying on the interaction forces, because if you look at the approach sequence of this contact mode cantilever, you are not exactly relying on van der Waals force anymore, you are actually relying on brute force repulsion. But see, non-contact mode imaging in principle relies completely on van der Waals forces, but in reality the resolution is extremely poor, and non-contact mode imaging is used, but in conjugation with contact mode typically for extracting certain additional interactions like electrical force microscopy or magnetic force microscopy, where let us say in electrical force microscope the scaling or the decay characteristic of the Coulombic force and the van der Waals forces are known to be different. Therefore, you generate different types of topographies from contact mode and non-contact mode, and you subtract them to identify the electrically active or magnetically active domains. Of course, MFM requires a magnetically a cantilever coated with a magnetic material. More important, which has become extremely popular these days, particularly because it gives you very robust data and it is very, very useful for polymer and soft materials and biological samples, is what is known as intermittent contact mode. This is also, even in many top journals, this is often referred to as tapping mode, but I would prefer you not to use the word tapping mode, though the world honestly realizes this mode as the tapping mode, but tapping mode is actually a copyrighted term of a particular company, and scientifically this mode is called intermittent contact mode. That is something that we will take up in the next class. This is very exciting, and I mean most of the samples people look these days, soft samples, even hard sample, tapping mode is sort of preferred because of many advantages, which I will talk. But one thing we haven't talked in detail yet, so this is some cartoon that shows the schematic of the contact mode, is about the scanner itself. So, it is a piezoelectric material. You can in principle have two configurations. You can have, so not only the scanner controls the vertical height or movement of the tip or the cantilever, but it also controls the lateral movement of the tip during rastering, because as I mentioned in the context of STM, maybe this entire area is 1 micron, and you want to generate data at 512 intermediate points. So, you can calculate that roughly you are seeking data every 20 nanometer. Now, which motor in the world is going to give you this type of precision? None of them are going to give. So, in fact, this XY motion is also controlled by the piezo as well as the Z motion. There had been designs, or there are still designs of AFM where the XY motion is controlled by two sets of piezos and the Z motion is controlled by a third separate piezo, but there are designs and which are becoming more popular that everything is achieved by one single cylindrical piezo. I will not go into the details of this thing, but except for the fact that I just highlight that this is roughly a cylindrical piezo, what is used in many of the high end microscopes these days, uses a single piezo with tube geometry. So, what happens if, so this has in fact 4 parts, you can identify that there are 4 quarter circular parts, right, which sort of constitute this tube, and each 4 sections can be made longer or shorter individually, right. So, you can feed the voltage, the feedback loop can feed the voltage individually to these 4 components. Now, you can understand if all these 4 components simultaneously shorten or elongate, then you actually have a movement in the Z direction. However, if let us say y, one of these components, let us say the y plus components elongates and the y minus component shortens, you actually have a motion in y direction. Similarly, with these two, with the help of these two, you can sort of control the motion in the x direction, and that is precisely what is done. This is something that if you want to understand in detail, you can read a little bit, but even if you do not understand much, it is perfectly fine, excepting the fact that there is only one piezo in most of the, in many of the instruments now, which uses a single tube like circular piezo element, and which has different sections which can be sort of activated separately or which can be addressed separately, and the voltage can be given separately. So, when you want to sort of move in the xy direction during the rastering, right. So, you have to sort of, if you want to move in the x direction, you simply feed to x plus, address the x plus and x minus, they sort of change their dimension and the tip moves in the x direction. If you want to move in the y direction, you do the same thing, y plus and y minus. If you want to sort of adjust the height of the piezo at every 2b, like when you realize that the new point where your cantilever has reached has a different elevation as compared to the earlier point, you sort of feed the voltage to the piezo in such a way that all the 4 sections expand or contract by the same amount, and therefore you have a vertical movement or either upward or downward to readjust the location of the reflected point to the set point value. Okay. And you can in fact, as I mentioned somewhere, that modern day instruments, it is in fact possible to choose the direction of the x and y, the fast and the slow axis, which may not be the actual orthogonal directions, initial orthogonal directions. That is simply because of the fact that you have the option of rotating the orientation of the whole assembly. So if you now rotate the whole thing, so let's say initially these were the 4 sections which was responsible for movement in this and this direction, and now what you have, let's say, is something like this. So this will be responsible for movement in this and this direction. So depending, there can be some interesting features for which you may want to change the direction of the scan, and that can be easily done using a cylindrical piezo element. There are models in which you have decoupled piezos for the x, y and the z motion. They also have their own advantages. You can have sort of individual motions, but it also comes with certain problems. For example, one of the major problems is if you have linear piezos for x and y movement, you cannot rotate this orientation of your fast and slow axis. Your scan will always be, your fast axis will either be in this direction or in this direction. You do not have any handle to rotate it the way you want. There is also another important thing, that is the maximum scan size. The maximum scan size depends upon the length of the scanner tube. So if it is longer, the scan range is big. If it is shorter, the scan range is small. Same thing is the length also determines the maximum height of the features that you can handle, and typically it is possible now to sort of scan areas as large as 100 micron by 100 micron in certain instruments with a maximum height of the order of, I would say, of the order of 10 micron. But you can, I mean, initially these numbers are very, very large compared to what was available initially, where sort of people could look maximum into 5 micron square areas with a maximum height of, let's say, 2 microns. So that also tells that AFM is not suited for very rough samples. Okay. So once the scanning is done, so this is something is, I mean, I will probably skip the different modes, the constant force and the constant height. It's very similar to what we have learned, the constant current and constant height modes in STM. Every sort of almost all contact mode imaging is done in constant force mode. I mean, nobody does it in constant height mode anymore, because in constant height mode you can in principle run it without the feedback loop, which is not done. So this is the one more thing that I will highlight before I end and break for today. This is the type of data you typically generate. There will be certain minus values, some will be plus, some will be minus, whatever. Again, something I missed out, and 1 1 should not have any value, 1 1 will be 0 0 0, right. So this is how you sort of split up your zone of interest, and you would like to sort of pick up the, as I have mentioned, you go on tracking how much the cantilever the scanner is moving up and down to which the cantilever is mounted. You generate this data file. Once the data generation is complete, all you do is you run a search algorithm on the Z column, find out the maximum value and the minimum value. You normalize the data with respect to that, and that normalized data you simply place into some sort of a grayscale, and therefore you see images like this, but these images are all digitally rendered, and this image in fact has no meaning in absence of this vertical scale bar, because the color code is simply corresponding to the grayscale you have used. It is not a grayscale, it is this type of color typically you see. But see here the color corresponds to the darkest area, corresponds to the deepest area in the sample. So, these are the deep areas and the brightest ones are the highest areas, and the maximum difference in height according to this image is of the order of 125 nanometer. Since you have data for all the lines, it is possible that you go to any line, you just ask for the section and you can get sectional image, sectional information like sectional profile like this. So, what you have got? You have recreated the contours of the surface and you now have absolutely true information in the vertical direction. So, this is an outstanding capability that only your atomic force microscope can offer, and it can offer because it sort of does not image or take a picture of the surface. It actually visits, the probe actually visits every point and picks up the information how much elevated or depleted that point is with respect to the point where the tip had initially approached. So, I will stop here. Please go through these lectures very carefully, and next class we will start discussing the intermittent contact mode or the tapping mode and revise some of the concepts that we have discussed so far. Thank you very much.